In this video, we're going to talk about how the Laplace transform deals with periodic functions. In the previous video in the series, we talked about how the Laplace transforms dealt with discontinuous functions, or piecewise defined functions, and in many ways, periodic functions are an extension of that idea. So let's just begin with the definition. A periodic function is one where you have some period p, and then f av t plus that period is just the same thing as f of t. You've seen examples of this before, for example, sine. This is a function that has period 2 pi. And what it means is that this graph of sine from 0 to 2 pi is exactly the same thing as from 2 pi to 4 pi, or 4 pi to 6 pi, and so forth. Well, what's a more interesting example? I'm going to construct a periodic function. So consider the function which is f of t equal to t, but it's only f of t equal to t on the interval 0 up to 1. And then I'm going to claim or assert for you that it has period 1 beyond that. So what does this look like? Well, if I just graph f of t equal to t, it looks like this straight line. But because of the periodicity, what I am saying is that this straight line is the exact same thing on 1 to 2, and 2 to 3, and 3 to 4, and so forth. So really what this looks like is just many, many copies of this straight line. Periodic functions like this are very common in science and engineering applications. Particularly, for example, you could imagine some signal that increases and gets shut off, and then increases and gets shut off, and so forth. So being able to figure out the Laplace transform of periodic functions like this is going to be very important to us. Let's begin generally. I want to imagine I have some function f of t that has period p. If I want to compute its Laplace transform, well, this is an improper interval from 0 up to infinity of the e to the minus st f of t dt, as we've seen before. This is just the definition of the Laplace transform. Now, the point is this. That interval from 0 up to infinity can be broken up. It can be broken up into 0 up to p, p to 2p, 2p to 3p, and so forth. That is, this improper integral is really an infinite sum of smaller integrals, each of length p. That is, I'm going to write it in the following way. This is an infinite sum from 0 up to infinity, so I'm breaking this infinite region into infinitely many pieces, but each of those pieces only has length p. That is, if you notice in my integral, the bottom of the integral starts at some number of copies of the period, n copies of that p, and then it goes up one more value of p to n plus 1 copies of p. Now, you might initially think that I made the problem harder. Instead of computing one improper integral, I'm now asking you to compute infinitely many different integrals. But we're going to use the periodicity of f to take these infinite integrals and all write them in a very similar way. Here's what I mean. Let's do the change of variables. T is tau, this new variable tau, plus, well, n copies of the period p, tau plus np. If you substitute that in, you're going to get the following expression. Okay, a lot of different things that happen. Let's focus on the integral first. If t was np, then tau is 0. If t is n plus 1p, then tau is just p. So I've replaced the limits of integration with something that originally depended on n with something that no longer depends on n, and that's going to be very important to us. Then the negative exponential, the t gets replaced with a tau plus np. The function of t gets replaced with the function of tau plus np. And indeed, d tau and dt are just the same thing, so I don't have to do anything there. Okay, so let me just focus on this result that I have. This Laplace transform of f is this expression. Well, f of tau and f of tau plus some number of integer copies of the period is exactly the same thing. This is like saying that sine of 0 and sine of 0 plus 2 pi are the same thing. As in, the definition of being a periodic function meant that it is irrelevant what integer value this n is, that's going to be the exact same thing as just f of tau, and so I'm going to replace it with that. I have the exact same expression, but just with f of tau now. Okay, now I'm going to focus on the negative exponential. The negative exponential has a sum in it, so the first thing I'm going to do is just break it up and make it a multiplication of two different exponentials. Now, one of these exponentials has a tau in it, and one of it does not. The one that does not have a tau in it, well, it is irrelevant from the perspective of the integral with respect to tau. That is, I can take the e to the minus snp, which is a constant with respect to tau, and move it outside of the interval. This is just going to give me the value e to the minus snp out the front, and then multiplied by this particular interval. Now, notice what just happened. That integral, it no longer depends on n any longer, n being the indexing variable in this summation. So I could just do that integral. There's one of them. I can compute it out. I'll get some function of s. And then it's going to multiply by this e to the minus snp thing. I'm actually going to clean up that exponential, and I'm actually going to rewrite it as e to the minus sp to the power of n. I'm just using exponential rules here. And the reason I've done that is that I want to see this as having two different components. One is the integral, which, as I suggested, is a constant with respect to n, just some function of s. But then what I have is a blah to the n, and that should remind you of being a geometric series. Indeed, the formula for a geometric series is that the sum from 0 up to infinity of r to the n is 1 over 1 minus r. We have a way to compute the value of this series. This works when r is less than 1, and indeed, because I have a negative exponential here, as long as my s is sufficiently large, this negative exponential will indeed be less than 1. And so I can just replace the entire summation with this value from the geometric series that just gives me 1 over 1 minus r, or in other words, e to the minus sp, and then multiplied by that particular integral. This integral is a proper integral. There's no infinities in it any longer. It's just something that hopefully we can do, at least if our f of tau is relatively nice. So thus our final formula here is that the Laplace transform of f of t is, well, this expression. Note, by the way, that this works for values of s such that this negative exponential is less than 1. All right, so that's our general formula. Now let's go back and look at the specific example we've seen previously, where you had this f of t equal to t, and you got the sort of sawtooth wave when you imposed the condition that it was periodic with period 1. So plugging into our formula, the p is just 1, and that's affected a couple places. So at the front is a 1 over 1 minus e to the minus s. Then it's an integral from 0 up to 1 of, well, an exponential times tau. Tau here because f of t is t, and then I'm using the dummy variable tau instead. So what's that integral? Well, it's not too challenging. It's one we have to do integration by parts on. There's a dv, there's a u. You can do that integration by parts and have the vu minus v du formula. I'll let you pause if you want to go and do this integration carefully yourself, but I'm just going to evaluate it at the 1 and 0, and then I get another evaluation at 1 and 0 I have to do, and this is my final answer. So here's the point. If you have a function that is periodic, the Laplace transform of that function basically just depends on your ability to compute a particular integral. The integral not from 0 up to infinity, but the integral from 0 up to p, where p is the period of that function. If you can do that integral, then you can compute the Laplace transform of that particular periodic function.